So let's begin. In the previous chapters, we've looked at how switches work, in particular, how they handle the forwarding of data using the MAC address table. We've also seen multi-switched networks where loops can occur, and we've gone through RSTP and STP that can be used to ensure that we prevent loops, that we have loop-free networks within our local area network. Now, in this topic and in the other topics, we are going to see how layer 3 devices use the network layer protocols like IP, the IP header, to forward data using the logical address. So in this particular chapter, we are going to look at the basic knowledge of IP routing. So frame forwarding. Frame forwarding, or the forwarding of frames and switching, has introduced the data link layer operations. So switches operate at the data link layer because they forward using the MAC address, and in particular the role of IEEE 802 based standards as the supporting underlying communication mechanism over which the upper layer protocol suites generally operate. With the introduction of routing, the physics that define upper layer protocols and internetwork communications are established. Internetwork communications. Please, just a reminder, please mute your mic. So, an enterprise network domain generally consists of multiple networks for which routing decisions are needed to ensure optimal, the best of the best routes are used in order to forward IP packets to intended network destinations. So this section introduces the foundation of which such IP routing is best. By the end of this chapter, you should be able to, Moroa.
Upon completion of this section, you will be able to explain the principles that govern IP routing decisions, explain the basic requirements for packet forwarding.
Wonderful. So let's do it. So the very first thing we are supposed to understand is what we refer to as an autonomous system, an AS, commonly referred to as an AS, an autonomous system. Now, generally, we have MMU who needs to connect to the internet. So in order to connect to the internet, MMU has what we call an internet service provider. In this case, KNet, ISP. Then ISPs will normally interconnect to form the wide area network. And in countries we also have what we call internet exchange points. So like they're used to interconnect ISPs between regions. And that is how we are able to really form the internet. So what's an autonomous system? Now, while MMU has a single router that interconnects us to our ISP interconnects several institutions of higher learning. So it interconnects KU, it interconnects, what do we call that one? Kabianga University, it interconnects UON, it interconnects many other institutions. So maybe here we have MMU. So when Kenneth is interconnecting all these people, actually all these routers belong to Kenneth. So this particular router that lies at MMU is actually a Kenneth router, and they are the ones that manage it, not our internal ICT guys. They don't have access to this router. Now, generally, an autonomous system can be thought of as an ISP or a group of ISPs, also known as network providers. So, for example, Safaricom can be thought of as an ISP or a network provider. Now, why do we define an autonomous system? Because in an autonomous system, the routers that are owned by one or more operators have a clear policy that governs how the routing decisions are made. They have a clear policy that governs how routing decisions are made. Most of the time, or let me say, hapo nyuma kidogo, it really meant, in fact, using a single routing protocol. A single routing protocol. So that is what really it meant. That all these routers are using the same routing protocol to make routing decisions. So what is a routing policy? A routing policy is a set of rules that determine how the traffic is managed within an autonomous system. The set of rules that determines how traffic is managed within an autonomous system. So I said that a few years ago, it meant having or using a single routing protocol. But nowadays, within the same autonomous system, you can use multiple. You can use multiple routing protocols. And you can use a feature we call route injection. So you can be able to learn routes. You can be able to inject routes from one routing protocol to another routing protocol. So if you do the professional level of this course, this is one of the things you're going to explore. How to inject routes from, for example, a protocol we call OSPF to ISIS. Okay, so let's move on. So I hope you've understood what an autonomous system is. So the local area network, the LAN. So we most of the time think of the local area network also as being a single broadcast domain, meaning that if a broadcast packet is sent from this device, then this switch will send it out through all the interfaces, and all the machines within that switch and that local area network are going to receive that particular frame. And most of the time, we don't want the single broadcast domain to be too big, because when the number of devices increase, it means the number of broadcast packets are going to increase because of the ARP request packet that has to be sent by each device, especially the gratuitous ARP. After you've configured an IP address, every machine must begin by sending a gratuitous ARP. So we don't want our LANs to have so many machines. So to break up our LAN into different broadcast domains, most of the time we use a layer 3 device like a router. Why? Because a router does not forward broadcast traffic. It does not forward broadcast traffic from one network segment to another network segment. What does that mean? In this case, if this one sends an ARP request packet, which is a broadcast, the switch will forward it to the router. The switch will also forward it here. This switch will forward it to the router again. This switch will forward it here. So what happens to the router? The router sees this is a broadcast, simply drops that packet. So the router cannot go ahead and forward that broadcast packet to this other local area network. It cannot happen. Now, what's the purpose of the router other than breaking down the broadcast domain? It's used to route packets from one network to another. So for example, when these two devices need to talk to each other, they are on different networks, so they need to go through the router. So that packet will come there, then come here, then it will be sent here, and finally it will get to this machine. So the router is actually the gateway. It is the gateway for each local area network. So this is one broadcast domain. Here, this is another broadcast domain. Because if a broadcast packet is generated, all these people in this circle are going to get it, including this one. This is one network. This is another network, LAN, LAN 1. So LAN is local area network, local area network. So LAN 1, LAN 2, LAN 3. Okay, so let's see, how does the router make routing decisions? So routers are responsible. Routers are responsible for the decision-making process that determines the path via which packets are forwarded. So in this particular example, we want to come to this destination. We want to come to a network that is here, interconnected to that router. So when we receive a packet, do we forward it through this route or through this route? So which route should we follow? So the router is responsible for making that decision, and this particular decision most of the time depends on what we call metrics. And these metrics are used to select what we call an optimal, the best, an optimal route. The metrics will differ depending on the protocol that we are using. So, for example, when we are using a protocol like RIP, the Routing Information Protocol, which we're not going to learn in this chapter, it uses a metric called hop count. Hop count is simply the number of routers that we're going to pass through before we get to the destination. So a shorter hop count is preferred. Then we have others like OSPF and ISIS, which I'm going to talk about in the coming topics. These ones use the link state, and in particular the bandwidth. So just to give a closer example, if a matatu is leaving Rongai for Nairobi town, there are several routes it can follow. It can either go through Kibera, or it can go to Timol, then Kenyatta, or Timol, then Nyayo. So those are three different routes. So how do they make the decision on which route to follow? So if you have a car, you can decide, I don't want to pass too many roundabouts, because at each roundabout, I'll have to spend like 5 minutes before the roundabout is opened by the police. So you can think of that as the hop count maybe. Then bandwidth. Bandwidth is the speed, the interface speed. How fast can it forward data? Is it an Ethernet interface? Is it a gigabit Ethernet? Is it a 10G interface? So with bandwidth, you can think of it like this, like these Rongai guys have touts at specific points of each of those routes who tell them the state of the road at any given point. So do we have traffic jam? If we don't have traffic jam, then we follow that route. So they keep on communicating with their phone. So routers work in a similar way in order to select the optimal route. So it is important to repeat again that these metrics will differ depending on the protocol that is used. So let's look at what we call the IP routing table. So far, we've seen the ARP cache table, we've seen the MAC address table that is used by the switches, and in routers, we have what is called the IP routing table. Now, if you're in a router and on system view, and you type the command display IP routing table, you should actually get the table, the IP routing table. Okay, so what are the contents of the IP routing table? The very first one indicates the destination network address and its mask. Destination network address and the mask. Then number two is the protocol. The protocol. So proto for protocol. So how did we learn? How did we learn about this route? So we're going to see the different ways in which we can learn. Then each protocol is associated with a certain value called the preference. So we're also going to see the different preferences for each protocol. The lower the preference value, the higher the preference for this particular protocol. So for example, the Manyanga drivers here, they can also ask their colleagues, hey, how is this route? They tell them, it's okay, haina jam sahi. On the other hand, they still have their boys who they are talking to. So who can they trust more? Their colleague or the boys they have placed on the road? So that is what we call the preference value. So whoever they can trust more will have a lower preference value, and they are going to trust them more than the other one. Then we have the cost. The cost generally is associated with bandwidth, and we are going to also see how the costing is done in the coming topics. So it is associated with the bandwidth of the interface. Okay, and then we have the next hop. Let me skip the flag there. So we have the next hop. The next hop. So we've already said a number of times that a hop is simply a router. So when you talk about the next hop, is the next interface, the interface of the next router that we are going to pass this packet to if we want to go to this destination. So for example, if we want to go to town from Rongai, our next hop can be Langata if we want to go through Kibera. Our next hop can be Timol if we want to go through Kenyatta or Nyayo. So that is what we call next hop. Then we have the interface. The interface here is used to represent the out interface. The interface through which, the outgoing interface, actually that's the word, the outgoing interface. So that interface through which we want to forward out that packet from our own from myself, that interface through which I want to pass that packet towards its destination. Towards its destination. So that is what we call the next hop. Okay, now when the next hop is actually 127, you remember the 127 that was left out between the class A and the class B IP addresses, 127. So then the 127 address range is used for diagnostic, and when we have the next hop as 127.0.0.1, it simply means that this particular interface is within this particular router. So it's just an internal interface. And indeed, you can see here that the outward interface, if we want to go to this network here, is actually loopback 0. So this is simply a virtual interface that we've created within this router. And that's why you can see here. So one of the protocols is what we call the direct route. Direct route is a route that is directly connected to that router, and it usually has a preference value of 0. So I hope that is clear. Can you be able to hear me? Someone is calling me. Are you able to hear me?
Yes.
No, you went silent for some few seconds.
Oh, sorry. I think someone was trying to call me, and therefore, okay. Sorry, I hope he's not going to call me again, because it interferes. It interferes with my internet connection. I'm using my mobile to Tether. Okay. So let's look at how the routing decisions are made. Okay, so I think there was a problem in laying out these slides, but generally this is how the routing decisions are made. We begin with what we call the longest match, then we go to what we call preference, then we go to what we call the metric or the cost. Actually, I like just calling it the cost metric, which is associated with the bandwidth. Then if all those are the same, we do what we call load balancing. So let's begin with the longest match. Let's begin with the longest match so that you can understand how it works. So in this example, we are in RTA, as you can see from this prompt. So if we type the command display IP routing -table, we're going to get the routing table. So the routing table is going to have networks that we are aware of. So these are routes that you are aware of. So for example, if you're coming from Rongai, if the only route to town you know is through Nyayo, you can't risk going through Kibera. Not even risking, you even don't know about it. So you just go through Nyayo. So those are the destination networks who we know. How we learned them, so the protocol that we used to learn that particular route. Did you learn it from a friend? Did you learn it from Google Map? Then each one of them has a certain preference. Then the cost metric, the next hop, if we want to go to that network, and the outgoing interface. So let me just explain. So in this particular example, we have this network here, the 10.1.1.0/30 network between RTB and RTC. So that network has been configured manually in this router. So that's why here on the protocol we are seeing static. So static is when we've learned a route manually. It has been configured. The route has been configured manually in the router, and the preference value for static routes is 60. Okay, so you can see that we have that network /24 in our routing table, and we also have 10.1.1/30. So that is what we want to look at. We want to compare the two way. Now with the longest match, just to mention, this particular route /24 and this one, they can one of them can be used to summarize the other. So that's why you can see both of them can get us to the destination through the next hop. So this is what we're calling the next hop here on RTB 20.1.1.2. So both of them can get us to this network where we want to come. So how does the router choose which among these two to use? So how the router does that is that it compares or does what we call the longest match. The longest match is doing a logical AND between the network address and its mask. So you do a logical AND between the address and the mask. So the one that has the longest match, will be the one that will be preferred. That route will be preferred. So for example here, this one that has /30, this one that has /30 will be preferred, this one. Because if you do a logical AND between this and this, obviously the one with the more number of ones is going to have the longest match. So that is how this route is going to be preferred over this other route, even though this route can also take us to that destination. So that is what we call the longest match. So now let's go to the preference. So with the preference, let's begin with the number of ways in which you can learn about a route. You can learn a route through what we call a direct route. That is, if you are directly connected to that particular network. Then we can manually configure a route. We call that static. So we have manual, we have direct, so directly connected to that network. We have static, we have manually configured. Sorry, I don't know whether you lost me again. Someone again was trying to call me. Then you have dynamic. In dynamic, we've learned the route through a protocol. So we've used a protocol. So some of the protocols we can use to learn dynamic routes include OSPF. We also have what we call RIP, and we have what we call IS, for example, IS, which you're not going to learn. And we also have another one called BGP, which you're also not going to learn. So we're not going to learn these three. RIP was there in version 2 notes. So if you want to learn it, you need to check the version 2 notes, which I also shared with you. But here we are going to learn about OSPF. Now, each of these dynamic protocols and all these ways are associated with a certain preference value. So for example, if we learn a route using the direct method, the preference is 0. the preference is 0. On the other hand, if we land it statically, then the preference is 60. If we land it through OSPF, then the preference is 10. And if we land it through RIP, the preference is 100. You might need to be aware that these preference values might differ from vendor to vendor. So this is what Huawei uses. So another vendor like Juniper might be using a totally different preference scheme for each of the protocols. Now, what you need to understand about the preference is that the route that has been learned using the protocol with the lowest preference value is the one that is preferred, as the optimal route. So in this particular example, when RTA receives a packet that is destined for this network, RTA can either forward it to that router or to this router. But now, how did it learn this path? It learned it through RIP. How did it learn this path? It learned it through OSPF. So, because OSPF has a lower preference value of 10, while RIP has a preference value of 100, the one that is going to be installed on our routing table and the one that is going to be preferred as the optimal route is that route that has been learned through OSPF, and therefore that packet will be sent through this route. So we're not going to forward via that route, we're going to forward it via this route. So we can see here on our routing table for RTA that indeed the protocol is OSPF and the preference value is 10. So I hope that is clear. Now let's go to metric. Let's go to metric. Now metric is associated with the bandwidth. Metric is associated with the bandwidth. And I think when we learn OSPF, we are going to learn it more on how the cost metric is calculated. Now, if this path has a metric of 100, while this path has a metric of 50, then we are going to use the one that has a lower metric value. Remember, at first, we check what? At first, we do the longest match. So if the longest match is the same, what do? We go to the preference. Now, as you can see in this particular example, the longest match are the same because both these networks, for this route and this route, both of them are /30. So the number of ones are the same. So the longest match are going to be the same. So it's going to look at the preference. When it goes to the preference, both routes have been learned through OSPF. So again, they're the same. So what happens? The tiebreaker now becomes the metric. So whoever has a lower metric cost is actually the optimal route. And therefore, what do? We simply install you in the routing table, So you can see here, under the cost. Under the cost, we've installed that one with a cost of 50. How can we confirm that? This is our next hop, 30.1.1.2/30, next hop. So we are not using the 20.1.1.2 next hop. So we're not using this. Instead, we are using that next hop. And again, just as a repeat, the interface. The interface is the outgoing interface. So in this particular case, the interface, the outgoing interface, if we want to go to this network, 10.1.1.0/30, this network, if we want to go here, the outgoing interface is this one here, Ethernet 0/0/1. Yes, or you?
Okay, I want you to assist me to understand this part.
Yes, please.
Okay, if you go check the next hop, I can see the IP is 30.1.1.2. Where
At when you?
If you check the next hop, we have an IP of 30.1.1.2.
Yes.
I'm like confused. I don't know where I've gotten the address to.
Okay. So generally, this is our network address between RTA and this router. This is our network address.
Yes.
So the assumption here is that this interface is going to be assigned the IP address of .1, while this interface here is going to be assigned as .2. So thank you for asking that. So this is going to be .2, this one is going to be .1. Okay, thank you. So I think now we can move on. Oh, just something else. Now the last bit, did you raise up your hand again?
No, I was trying to lower it.
Okay, now if all these match, the metric has matched, the longest match, preference and metric have matched, it's going to do what we call load balancing. Now, what does that mean? If this guy here, so if this guy here also had a metric of 50, this path also had a metric of 50. So the router will actually do load balancing. Load balancing is send some packets via this path, send some other packets via this path, 50-50, 50-50%. So that is what the router will do as the last routing decision, load balancing. If all these three match, if the first three match, they're the same for the route, then go ahead and load balance. Okay. So I want us to finish this.
Yes, excuse Chris.
Yes, go ahead.
Can you repeat on the load balancing kidogo?
Okay, so let's use this example again. So if the cost for this path was also 50, sawa sawa?
Yes.
The cost for that path is 50. I don't know whether, am I able to erase this? I'm not able to. Okay. I'm not able to erase that 100. So just understand that the cost here is 50, the cost here is 50.
Yes.
So this router has to make a routing decision. First, it will check what we call the longest match. So both routes have the same longest match. So after the longest match, it's going to check the preference. Both routes have been learned through OSPF. So the preference value for both routes is going to be 10. So again, the same. So after that, it's going to compare the metric. Again, the metric are the same.
Yes.
So once all those are the same, it means that no path is better than the other. They're equal. When they're equal, just send some packets over this route and send some other packets over this route. So load balancing is simply, you share the task. So if you have 3 interfaces, you share, I think 33.33, so that no one is doing more than the other. So if we have 2 interfaces here, then we're just simply going to share 50-50.
Now I understand.
Wonderful. Okay. So I think I've already mentioned most of these things. So this is how routers learn routes. So a directly connected routes. So for example, this interface G001 is directly connected to this network 10.1.1.0, directly connected. So that's a direct route. Then we can also configure a static route. That is, we configure a route to this network manually. So that's what we call a static route. So the route will have the destination network and the outgoing interface. So for the direct route, if we want to get to this network, we go through this interface G/0/1. Then we can also learn routes using protocols. We call it dynamic. For example, this route 192.168.2.0 has been learned dynamically. If we need to go there, we go through the outgoing interface G/0/0, this guy. We go through that. So let's look at the routing table forwarding requirements. We've already talked about this. Oh, someone else is calling me. What is happening? I'll just call them in a short while. Okay. So there are things that the router must know in order to be able to forward a packet towards its destination. So the first thing it must know and be aware of is the destination network. Now, if this router does not know, if it checks the destination IP address of a packet, it calculates the network address, then finds out that it does not have that network address on its routing table, it's going to discard that packet. So that's the very first thing that the router must know in order to forward a packet towards its destination. Do I know? Am I aware of this network? It's just the same way. From Rongai to town, you don't know the Kibera route, so you can't use it. So the routers, same way. I've received a packet, it's supposed to go through Kibera, but I don't know Kibera. So I drop it, I discard it. Now, other than the destination network address, the router must also be aware of the next hop, that is the next interface to which it's supposed to forward it to, and the outgoing interface, the interface via which it is supposed to forward out that packet towards its next hop. So those are the requirements. Those are the forwarding requirements for a router. It must have those values, and we've already gone through those values in the routing table. Okay, so I want to choose 2 volunteers here. Who has not spoken since morning to help us in answering these 2 questions? Michael and Benson, have you guys spoken today?
No. Hello, can you hear me?
Yes, we can hear you. Just move a little bit closer to your mic and go ahead.
Okay. What is the order in which routing decisions are made? The first one is the longest, then followed by preference, then metric, then load balancing.
Then?
Load balancing.
Okay, thank you very much. That is correct. Your voice is a little bit low. I don't know why. During tea break, did you take something?
Yes.
Sawa. Benson, you can go for the next one. If Benson is not ready, we can hear Lynn.
The preference, it represents certain routes that have a preference value. So the router chooses the one with the least preference value.
What is the preference associated with? The preference value is associated with?
I'm not sure.
Can I answer that?
Yes, please.
With OSPF.
So really, the preference value is associated with the way the router learned that route. Is it direct? Then the value is 0. Was it configured manually? Then the value is 60. Did we learn it through RIP? Then the preference value is 100. Did we learn it through OSPF? Then the preference value is 10. So don't forget that. Very common question again in the exam. Thank you very much, Lynn and Oyo. So we move on to the next topic.